Thank you very much for both the local ones and the international participants. Good. We were discussing whether we do it in German as we are in Aachen or we do it in English as we are international. So let's do English. The other, I'm supposed to talk something like 40 to 45 minutes. Some of it will be a little bit of a film because kind of I wasn't doing enough choices. And originally I thought it's a 2-hour slot. So the second hour will be out in the garden for those. We will see whether we find a good Wi-Fi there for the internationals to participate. Good. What are we talking about? It's a talk I've kind of given a few times. The concert hall, is a concert hall a machine for music or is it not? It's kind of one. But here we want to focus how to integrate acoustic design into architecture. We were just talking that architecture is totally linked to what the acoustic result is. You give an auditory scene of a staircase, somebody walking down a staircase, to an architect, and he directly draws a staircase. So what does that mean for acoustics once you're doing room acoustics design? Oops, that goes to this one. Yes. Concert hall, a machine for music. That's the Concertgebouw in Amsterdam. That was the last ISRA meeting. What is that one telling us? Basically, that's a 19th century concert hall. It works perfectly well. It still exists. It's still one of the best rooms in the world. Why do we want to do research and why do we want to make life complicated? Actually, that is not the original room. Even that room has been transformed 3 times. And what is even more important is that the orchestra was transformed. Concertgebouw was actually rated quite badly when it opened, the same as Boston Symphony Hall. And there is a very easy reason for that one. Concertgebouw, when it opened, was about 80 musicians. Boston was worse. Boston Symphony Orchestra was 35 musicians when Boston Symphony Hall opened. And figure what? It wasn't quite loud enough for the 2,500 people. Good. We actually at Kahle Acoustics, we have a bit of a motto. Now, does it work on that slide with a blueprint? I'm not so sure, but just fine acoustics is not there to be seen, but should blend into the architecture. And I'll get back to that image or corresponding image. Actually, most people, when they see this image, think of architecture. Every single surface you see here is shaped acoustically. And as Michael said, how do you convince an architect that the architect believes he drew it when in fact it was drawn for acoustic reasons? And it's half this is true, half it's totally exaggerated. I normally say I like projects when in the end I visit the room together with the architect and we look at each other. Who did that one? Wasn't me. And actually, sometimes you find out that you don't actually know who did what. One I'm talking about, which was already in the abstract, it's Philharmonie in Paris, and the other one is on the left side at the bottom is KKL Lucerne, 2 projects with Jean Nouvel, so 2 projects with the same architect, totally different shape, totally different attitude. And I'll go to that one. That was more another talk. All of what you see is ceramic tiles. Can you actually do a concert hall? The other one was always, can you do a concert hall that's all glass? Can you do a concert hall that's all ceramic tiles? The answer is yes, if you think about it. But let's go back to the machine for music. The first thing I already said, there is musical needs. And here I'll be very quick. That's a slide I like to do at the introduction. That's the chapel in Versailles. Why is the chapel in Versailles important in a talk on concert halls? Because actually it's part of the history of French Baroque music. The chapel in Versailles means it's the composer of the court of Versailles, which was the most prominent musical position of the time. So there was wars going on about who is the Hofkomponist in Versailles. And there is a very clear influence of music in Versailles before that chapel and music in Versailles after the chapel. At that time, composers were composing not only for rooms, they were composing for events. And here, this is Villa Aldrovandi in Bologna. That one is a more known example. That's Esterhazy Castle. So here Haydn moved in his life from one room to the other, and that is actually Hanover Square in London, and he was composing for specific rooms. And actually has two consequences. The first consequence is in the historic times, it was up to the composers to do a composition that is well adapted to the room. And now, what are we doing? We're doing concert halls that need to be well adapted to the program. So if the program is fixed, I can design the room for it, but most of the time we'll see in a second, there is no such thing as a fixed program. And I sometimes say if a client tells me I'm doing a room for chamber music only, there will never be any amplification in this room. I just say it enters that ear, it goes out the other ear, and I forget about it. And it's not because I'm nasty, it's because I've learned. I've listened too many times to that one, and every single time it has proven wrong. Nobody ever does a room that doesn't do amplified music. Good. The second part of the history is why I use that one. That's actually in Paris, the Église de Billette, which used to be a Protestant temple. And the fun thing here is, what are we talking about? We are talking about actually a shoebox room with wooden balconies and superpositions. Another historical precedent, or rather another example of rooms for which music has been composed. And that gets us more into nowadays times. No, this is still quite old. This is 19th century. That's Musikvereinssaal in Vienna. The joke is it only sounds so great because it's so golden, and you have the golden caryatides, the statues. Ingo, where is the measurements like Concertgebouw that tells us the influence of the heads of the pillars? I want to see that one measurement and how different it is to Amsterdam. I actually believe that the caryatides are important, but they don't need to be bare-breasted women, and they would still do acoustically. But the interesting thing is, what is it that makes it? Is it the statue? Is it the top connection of the balcony, or what exactly is it? We will cook. There is another PhD thesis, but that was on outdoors, but he could tell us something about that one. Good, so that's the bare-breasted women. The other important one is that if you go to Vienna and you do a guided tour, they tell you that seat was the special seat of Johannes Brahms. And then you start thinking, Johannes Brahms' symphonies were he never had a first performance of a symphony in Vienna. I come from Karlsruhe. They're very proud that Brahms' first symphony was premiered in Karlsruhe. But I don't think that was Brahms's wish. He would prefer to have his symphony in there, but he wasn't invited. But what it means is, when he was composing symphonies, that's what he had in mind as an acoustic scene analysis or acoustic quality. And that's why his symphonies sound so great there. Good. Now we go to the 20th century. As said, I'm going to say something about KKL Lucerne. Actually, KKL Lucerne is a contemporary extension of Musikverein Vienna. You see it very clearly. Side balconies, undersides of balcony, the soffit reflections, the famous German Winkelspiegelreflexion, cornice reflections. In Lucerne, we have 1,900 seats, so it's bigger. So we have 4 side balconies, which actually makes it more efficient acoustically. And then we get into the machine of music, and that is, it doesn't only do Brahms symphonies. One of the specialities in Lucerne is the very big things, from Mahler symphonies to Bruckner to Shostakovich to Strauss. So what does that mean? Here in Lucerne, we actually have the inner shoebox surrounded by an outer volume. Oh, that gets complicated to do coupled theory and all that one. We are going even further. We have the outer resonance chambers that have variable acoustics in them as well. But basically here, I want to go to something much easier, much simpler, and that's actually how we use these chambers. The inner room is 22 meters wide. The outer room is 30 meters wide. You have 52 doors where you can open it. So what do you actually do? Luckily, they open in a way that creates nice projection out to the audience. So that one you're using as well. But to a certain degree, I have a room for which the stage has a variable width. And I can choose whether I want to have the inner width of 22 meters, or I have the outer width of 30 meters, or kind of everything in between. And the main setting of Lucerne literally is a smaller, denser setting for chamber orchestras, a more open setting for symphony orchestras, and then the extreme. Basically, the bigger the orchestra gets, the more you open the doors, and especially the more you open the doors close to the musicians. The musicians hear it instantly, and you hear it instantly in the hall. Once you have it closed, a Mahler 8 is a little bit tight. And then you open it, and you have means of correcting. Good. What does it actually mean for all of us? And that's kind of my first, what I'm in the train here, I thought actually there's another title of the talk, Drop Your Preconceptions. I'm trying to destroy some preconceptions in this room. And the first one is, there is a paradigm shift between the Baroque music where composers were composing for a specific, as I say, event. They knew who the performer was, who the listeners were, and what the room is. To now, we are building concert halls for a program that used to be, in my parents' generation, from the late Mozart to possibly the early Mahler, or the late Wagner was already the borderline. Nowadays, in Lucerne, program is 12th century music, 13th century music to contemporary. Any concert hall basically does 500 years or 800 years of musical program, including brass bands, amplified music, congresses. So that's what we need to design for. And we have to really look quite carefully. What does it mean? And one is size. I can get to that one. That's a long discussion. I have a second presentation, but I don't think I'll get to that one. Size matters because there is something, loudness is always positive. Anybody who sells loudspeaker equipment knows that a dB extra is worth quite a lot of money in comparative listening tests. If you do that in a concert hall, said that one in Aalborg, it's actually Jens Holger Rindl who has this 85 to 90 dB for the loudness for Forte of, he says, a symphony orchestra, but I actually think it qualifies for nearly everything. And then it's been transformed into 90 dB plus or minus 5, and I actually believe it's wrong. It's 85 to 90, and the preference goes up. The louder a concert is, the better it is. And then the cliff is very steep on the other side. If it gets too loud, oops, sorry, I can't take that one, I'm leaving. I'm sometimes giving this example of, we'll see how many people have still the experience of taking planes. Has anybody had that same? When there's a security announcement in the plane, there's a certain loudness level, and in the middle it goes up. Because I think somebody figured that one out, that people lose concentration and you have to wake up their concentration again. The second part of the announcement is louder. And I always find the second part of an announcement aggressive, or it depends where I'm seated. If I'm right under the loudspeaker, it really is, what is this now? The first one is fine. The second one is just not acceptable. And the same actually happens, I think, in some concert halls. Once it gets too loud, sorry, I can't take that one. Good. The other funny one that comes from that one is, what's good acoustics? And that's always a long question, what's good acoustics? And it's a question I can ask anybody. But actually the mission or the message is, you cannot define good acoustics. Try. Some people have done, sorry, stupid arguments that get me angry. As has been shown, the linear decay is what sounds best. Can somebody please tell me why? Because it looks best on the graph, because it's the easiest way to make a regression curve. Perhaps, yes, we are engineers, or we are engineers amongst other things, but there is no acoustic or musical explanation. So actually, acoustic quality is a very, very easy definition. What sounds best, what people like. Nothing else counts. And it actually goes with taste, and it's something for me. I kind of think what my taste is. Luckily, my taste seems to be what other people like as well, but you cannot define it objectively. I mean, you can, but you have to start by, I have to ask people what they want, and then you get into the criteria, and then you can optimize, and you always have to ask yourself the question. Good. Number two is basically the machine of the user's needs. That one, you can't go and visit any longer. There's too much asbestos behind it. It's a total scandal. But that's what you thought is the nec plus ultra of variable acoustics in the 1970s. A reverb time that can be changed from something like 0.3 seconds to 2 seconds. Any computer does that one today. It doesn't even have to be a high-powered computer. I mean, varying reverb time, varying acoustics, we know it. I always found that room actually extremely limited. It is a cuboid. It can't do anything but a cuboid. It doesn't have any side balconies. You can't even create reflections. It always sounds like a big bathroom or a big dry room. Good. Anything better we can do? So that's what is all done. And then a colleague of mine came with that slide. Does that one ring a bell? I'm too old for that one, but that's his toy from school. Can we do variable architecture? Can we do a toy that, just like that toy that starts as a car and then becomes a robot? Can we do that one with a concert tool? Answer is yes. But what you actually have to do is something like that. Something has to move. Good. What do we do? That's an easy one. Luzerner's, that's the second room in Lucerne. That most people still know. Raked seating, retractable. So it can go from that. That's a half raked seating with half flat. And then it goes to banquet. And then it goes to car presentation. As I always say, sometimes you have to earn some money. It's just a fact in life. And as long as the money is well used to actually have some real culture afterwards, I'm fine with that one. Good. So that's just the seating. That one we're pretty used to. Can you do more? That's a project I did years ago. That's a multi-purpose hall in Dole. That's so multi-purpose now. Dole is a city, village, town, whatever you want to call it, of something like 25,000 inhabitants. Can we have our cultural center that does classic concerts, amplified concerts, theater, but actually it should do professional sports as well, because it's the only thing we can build in the next, whatever, 20 years. And the answer was, I then ended up with a hall that was 45 meters wide, because that's the architect and actually the logical decision to make it the sideways and then stick a stage house on one end. And I said, they are asking for intimate theater. I'm sorry, I can't do intimate theater in a 45-meter wide room. And has nothing to do with acoustics, but just by intimacy. So that's the big one. And that's how they use it for congress. And actually, all you see in the sidewalls move. And they move extremely simply. I'll just do it here on that one. You see the roof trusses. The roof trusses are beams. But basically, the only thing you do, you put a rail on the bottom end of the roof truss, and you do an inverted stage set. So basically, it's a triangular thing, and it just goes down. And actually, you put that one on wheels, and you can push it by hand. No, this is actually motorized, but it's not a wall that is doing any acoustic isolation. That's the important one. It just does room acoustics. It doesn't do the acoustic isolation. But if it's just the room, a motor can do a lot, or actually just shifting things around. So that one is 45 meters wide, and this is what doesn't really work too well, but you just see it goes around, it goes smaller, and it goes even smaller. And to have the fun, you can have, that's the wide one. You could even turn the room 90 degrees around, and then you have a nice shoebox. So basically, it has a variable width from 45 meters to 18 meters on simple tracks. Actually, scientifically, it's possibly one of the most complicated rooms I've ever done, because above the tracks, the two volumes are coupled. So you're talking about coupled volumes where each volume has variable acoustics absorption depending on audience occupancy, and the volumes are changing. Have some fun. It's not that complicated. Good, so that works. And that's a low-cost project, so that one works. That's a high-cost project, not of mine. So that's the Concert Theatre in Muscat, where basically they wanted a full opera house, and then TPC did the study, and they said, basically, you don't have an audience and you don't have an opera company. So are you really sure you want an opera house? But what you do have is you do have an orchestra, and you do have an audience, and you have the local music. So then they agreed, yeah, let's do the concert theatre. It does both. And you can kind of, that's all the scale model, because it's fun to look. So that's, you see the plan. And let's just do this one. This is what happens. Then it moves back, and it moves even further back, and the stage set comes in. So basically what's happening is all the stage end and all the stage is a train. Not actually, if you think about it, not that complicated. This is Muscat Oman. Any container ship terminal does more complicated things than that. And this is just zip, you just push it back. The only thing that is problematic, it's actually rather costly, because most of the backstage is actually a very expensive storage place for the stage. But other than that, it is possible. There is other things like the proscenium boxes actually rotate, because the proscenium opening for theater and for concert is not the same. But once you really start about thinking about variable architecture, suddenly you can actually do quite a lot. Good. That's another one. That's Cerritos Los Angeles. Basically, other than the little rail here in the front, everything you see in this image moves. All the seats are towers that move on air casters, and back there you have a retractable that is on air casters, and all that can basically shift around, so they do various shows and exhibitions. Amazing. Oh, this is just the special ones, the multi-purpose and the congress halls. Ingo just said he visited Philadelphia a few years ago, but the years don't count, so it's a few months ago, and that it basically looks pretty run down after 10 to 20 years. And I told him I have the explanation here, because this is Philadelphia. 2,500 seats shoebox concert hall, which is a bit problematic, because 2,500 for a shoebox, it's pretty tough to get all the people in. The room is a bit too wide, the balconies are too deep. Let's not talk about that. But Philadelphia, they quadruple their concerts. Philadelphia Orchestra, they have one of the best music schools. They have another orchestra. They have invited. You see, if there's one place in the world where you can actually build a concert hall just for symphony orchestra, yes, a piano every now and then, it's Philadelphia. Good. That's what it's built for. That's what the opening concert was. Somebody cooked up the money to get Elton John into there before the Philadelphia Orchestra. So what you see here is 3 tons of sound equipment and 20 tons of light and video equipment. And luckily, the theater planner had planned for this one, so the building was still standing up after that one. But that was the opening concert. Here, another show. Look at the little line array. That's basically, do you need that one for a classic symphony orchestra? No. Do you need it in general for a concert hall? Yes. That's what they do as well. And that one is the nicest one. How about Holiday on Ice on the concert hall? I mean, welcome to, what is it, Aachen Concert Hall at the International Congress Center. You can take it into consideration. Whether it's a good idea for how the building ages is another question. But basically that you can do it. And now I get more to how do we actually do design optimizations today? And I didn't want to talk too much about that one, but visually it's just interesting because this is what you do nowadays. And on computers, it's always difficult to show what a computer does. But sometimes it's actually easier to show it differently. That's a fun phrase. I like the best buildings you'll ever hear. That was the architectural critic page of the New York Times. When the journalist says the best buildings ever, he's not talking about acoustics. It's just the most beautiful new generation buildings. So we care about architecture. Okay, so what do we do as an acoustician when everybody cares about architecture? We start working. Good. So Philharmonie, we'll see some others, but the clouds we've seen there. How did it start? Because basically the development of the Philharmonie de Paris is in parallel with the development of all these computer programs. So it started that was Marshall Day, that was still Howard Marshall, that was the design from the competition. That's the clouds we found beautiful. Are they good? Give it to me. And the first thing Harold did is show which are the most important parts of it. And the second one is, for each point, he defines, now this is acoustics, 2 angles. So the orientation of what it needs to be to do an efficient reflection. But basically there it was what we called the points. It's the definition of a point, or rather the definition of the orthogonal of the surface at local points. And now you architects, you have these intelligent programs, you can connect them and do something that looks beautiful. Good. And there, that's why I'm showing it. That was the acoustic scale model. So that was the model of the model. So that's 1 to 100, and that's 1 to 10. You can walk around in there. And that's kind of what I want to get to is, you see all these things here? That's actually all mirrors. It's aluminum foil that you stick on, and then you take a laser pointer and you literally just try to see what happens. Can I do the same with the computer? Yes. That's actually how we started. We love Rhino. We hate SketchUp. Don't ask me why, but it's historic reasons. Rhino had in one of the first versions a function called bounce. And bounce is just doing a mirror. So that function of sticking something on the surface as a mirror was directly integrated. As one point, it draws you a line and it draws you the line back. Oh, interesting. And then you try to do bigger ones. And the initial ones, we used the surface, we meshed it, we took the points and run the routine. And nowadays, we basically would take each reflector as a whole thing, select, tell me what it does, and tell me where it all goes. And then you have all the things. How late does the reflection, where does it get to, what we call the lost rays? Do I show the lost rays of what happens, or do I not show the lost rays? What's the delay in milliseconds? What's the strength? And then what we internally do, what is the strength, what we call delta L curvature, which is once again Barindel. Is it stronger than the straight reflection, or is it weaker than the straight reflection? Good. So here you can see, and you can very clearly see, by shaping, rotating all these surfaces, you can more or less do what you want to do. And I'll go to the preconception in another slide a little bit later. So here you just see just some more model shots, and that's the fun bit of the room. Some of these surfaces are so shiny. I always use that photo because this is the canopy reflector, but it's on stage level because it's still being finished as construction. But on the top, it has this lighting ring. And basically, whenever you see a light reflection in one of these surfaces, it means there is an acoustic reflection. So it's actually just showing what. And Thomas Selot has done exactly the same on the Rhino model. And he now actually does it in, Thomas is, I think, the one who is not in the Zoom, but he's back in New Zealand, so it's the wrong time zone. Good, so what he's actually doing is color coding. So what's happening for the strings, what's happening for the woodwinds, what is happening for the brass, so that you can even see this, because you just define the zones. Good, I said some of it will be film. Good acoustics is not there to be seen. It should be part of the architecture, but the reverse is true. Anything that an architect does influences acoustics. So anything an architect does, there may be an acoustician who says, can't do that. And that's what I like about collaborations. The one English phrase, they're not. It's no longer politically acceptable, but there's always different ways to skin a cat. So what I find is when there is a proposal by an architect that just isn't possible, you say no, and then you say, we discuss. There will always be a different solution. But the same holds for me. When I say I want it that way, the architect, that's ugly. There must be another way of making it to actually get to the same result by different architectural means. And good acoustics needs commitment from the architect as well as the acoustician. Both sides have to discuss, and both sides have to be open and creative. And I just do an example of what is hopefully frustrating you a little bit or waking you up a little bit. That's the stage and gate sets. That's actually the rendering, just to not give away. That is the view from the stage. And that is the view of the stage that we've already seen earlier on. And that's the fun image. What's the difference between the two? What's the architectural freedom of a shoebox? Is there any architectural freedom? I mean, basically, look at this one. Yes, one has 4 balconies, the other one has 3 balconies. They're pretty much exactly in the same locations because they have to be in the same locations, otherwise you can't see. The height is pretty predetermined because we need the volume. The length is pretty predetermined because it's the seat count. Actually, the kind of shocking conclusion is there isn't a room that has less architectural freedom than a shoebox. The only thing you can do is paint it and choose some materials. And then you can say the acoustician basically has a fun. It's like somebody, you can't get a 20-meter wide shoebox wrong. But the price you pay is a ton of set of constraints. And I think it's basically, it's just a different set of constraints. Philharmonie Paris is a full set of constraints because the few reflection surfaces that exist need to be optimized. Good. Creative architectural shapes are not necessarily giving more freedom. It's a definition of what you call freedom and which freedom you want. Good acoustics needs to be integrated, but constraints can actually be happy constraints to spur creativity. And then comes an important one that I don't actually have the answer to. Stefan Weinzel is doing some studies. What sound do we do? What sound do we actually want? Now that I have all my reflectors that I can curve in, can I take the impulse response of, let's say, KKL Lucerne and make Paris sound the same? And the answer is, more or less, I can. Do I want to? That's the interesting question. Do I actually want that the vineyard sounds different, or do I want it to be a clone of a shoebox? And I actually think I don't want it to be a clone of a shoebox, but it's not necessarily that every vineyard sounds like Berlin Philharmonic. There is what I now call, there is personality of concert halls. And I think every concert hall should have specific personality, and every concert hall can be better for some things than for others. Should all sound good, but you really have to think about what is the aim. And that's back to the same subject. That's Fuzhou. This is the ceramic tile opera house. So that's the Rhino ray tracing. No lost rays here. So it only shows the ones that do survive. And the important thing here was we did another one that was much easier with the same architects in Pesach. We are now doing a new one. That's when they used T-splines. The nasty one is if you actually change the curvature here, something else happens on the other side of the room, and you try to understand how can I optimize something without fucking everything else up. But it took us a little while, but then we managed. Of course, this is an opera house, so there's tons of side lighting positions integrated there. And we love side lighting positions that always eat the sound and don't really do what you do. So we designed the reflectors around the side lighting positions. So that's the optimization of the reflectors, that basically that transition zone nicely covers the main floor. That one does the first balcony, and that one does the second balcony. But that's great with this architect. They do everything in Rhino. They love if we fuzz around with their models. And in the end, you literally don't know what is happening. So all of this beautiful architectural image of that one, all you see is actually designed acoustically, no. Checked acoustically, yes. Optimized acoustically, most of it. And it's always a back and forth. And that's what I want. That's one of my main messages, that in good integrated acoustics design, behind the architectural image, there's a grid of functional design. It's a grid of functional design because you do need the lighting bridges. If you don't do them properly, the room doesn't work. You do need acoustics, and you do need some other things, from thermal isolation to everything. And that done, I'll just very quickly go through. Yet now it really gets to Phil. Increasing the toolkit is something I've been thinking about quite a lot. Exactly. What can you do if it's not a shoebox? You can either say, I'm stuck, or you can say, I'll try and see whether it works, or you think about how I actually do it. That's the same about that one. Philharmonie Paris is already a mix of everything because it does have balconies on top of other balconies. So the lower part of Philharmonie is actually mainly designed as a shoebox. It's only the top that is designed as the directional design. Well, let's break it down. That's the shoebox design. It's balconies that go against the wall. What I've already taken is I don't do the entire wall. I only take the underside and the relevant bit of the wall. Doesn't actually have to be the wall, can be anything. Stavanger, we've actually, because the room was too wide when we started, we've taken the entire balconies and shifted them in by 2 meters to make the room more intimate. So what we've done is we've taken the important reflector with it. We've actually done that one in a scale model, comparing with and without the reflector. And luckily, the answer was the right answer. Taking the reflectors with you is best. Good, so that's easy to understand. And I say very often, acoustics is playing billiard. Not that I'm tired of playing billiard, but I don't do it that much any longer. But you can make more complicated billiard. How about we do more complicated billiard? I often say, if the billiard is at 90 degrees, I can now, after a few years of experience, I can do it in my head. So that's actually Stavanger, that's the balconies. So that's the typical one. And then first thing is, what happens if I rotate this one? Very funny, nothing. A 90-degree angle is always a 90-degree angle, and it actually tells you a lot of things. It's a 90-degree angle is always going back to the source. So if you want to do self-hearing, do 90 degrees. If you want to avoid self-hearing, don't do 90 degrees. We get to that one. Now that is 93 degrees. So you don't get anything back, but you get it to, it depends how far the distance is. But basically, once you have the computer program, you know. So you can do 90 degrees, you can do 87 degrees. Here, now this is the overlap, but then it crosses and goes somewhere else. That's 84 degrees. Then we're back to what it was. How about that one? Curving. You can't curve. Yes, there is a total focus point. There is a great focal point, but 2 centimeters away from the surface. It's not very likely somebody will stick their head in there. And once you do that one, that was an intern, basically student. If you curve, you can define how much you want where. If you have a 20-meter wide parterre, you can define, I want equal coverage of the 20 meters. Good. That's increasing the toolkit. We've actually done that one because that was Bordeaux, a crazy shape in an existing space, and we go to all the neighbors and then stick the balconies. And then we took those optimized reflectors because we didn't have enough surface. So we needed to curve them so that we can create the reflections. And you can kind of see it's all curved here. Good. That's the balcony fronts that most people have never really thought about. And that's vision, so that's vertical balcony fronts, and then everything always traveled up. At the moment I do inclined balcony fronts, I can basically decide where I want them. And that's the ray trace. Balcony fronts are great things because basically you can do tons of things. You can angle them in plan, you can angle them in section, you can do tons of things. And nowadays, this is just a superimposed image. It's just the idea of, in a Rhino model, I can just take a surface. And by now, we're not doing Rhino, we're doing Grasshopper, we're doing everything's interactive. So not me, but my collaborators. And then I say, can I have this surface? And can I do a radius of curvature on there? And can I angle it again? And all that happens in real time. And you can basically then look at one surface after the other. That actually allows you, and that I think about the last one I will do now, that allows you to think about curved surfaces very, very differently. That's, I hope, what you've not been taught in Aachen, but unluckily I fear that what you've been taught, because that is still common knowledge. Convex surfaces are always good, concave surfaces are. Don't do it. They're bad, they have a focusing point, they can create problems. It's true, they can create problems, but they don't have to create problems. How about these rooms? They're all bad. Left is La Monnaie Opera House. I live in Brussels, so it's where we hear most opera, and I love it. The right one is Kulturkasino in Bern. We just renovated it, and it works just fine. Worst one is that one, Wigmore Hall, that's from Thomas. It is full of focus points. It has a barrel vault ceiling. You see what it does. Wow, that really looks bad. It's the preferred chamber contact hall in London and in most of Europe. So actually, it goes worse than that. It is not only that concave surfaces are not necessarily bad. Concave surfaces can be part of the reputation of a hall. And that one is complicated because if you're doing it with a full symphony orchestra, then it's complicated because I have a focusing on the clarinet, but not on the oboe. Then I have a real problem. That is chamber music. Therefore, it more or less works. But it's interesting to think about it. But then that's where the computer programs get helpful once again. The moment I have a variable radius of curvature, then I can really think about what I want to do. And that's just kind of, that is what happens in Bern. So there is focusing, it bundles it in the middle. You can't hear it. We have a little problem because people here complain that it's less good. Tell me why. Go down, that's kind of inherent in it. That was Wushi, that was the first one, which was not T-spline, that was full Rhino. The architect wanted to do 19 bands superimposed. Can we do that one? Lots of convex and convex shapes. Yes, they overlap, and basically you can do tons of cornice reflectors. And that is just the final image of how many reflections can you create from some crazy shape. And all that is nice lateral imagery. Good. Von Oscar is on the call. So basically, that's Von Oscar's project while he was at Kahle Acoustics, that's Opera Nation in Geneva. What I say is every architecture design is different. Everybody asks us, why are they so random? Do they have to be random on the wall? No, that's the two proposals we did. One was an orderly one and one was a random one. And the architect absolutely wanted to have the random one. So then we do the random one, and then basically each color is a color code of where the reflection goes. And then it's just very easy, you shape them around. And we'll be quite proud of that one. It was a very good, it's all done in wood. And the people that built it actually used our 3D Rhino model to cut the wood pieces that are required to stick the reflectors on. Just CNC machine one night, bolted, and it's actually more or less identical. What you draw in vinyl is what is constructed on site. And that's just the last one. That's actually one I did with Juan Oscar together. That's Bochum. It's a shoebox, and basically has no 90-degree angles, and it has lots of curves. Half it's the conductor who wanted the surrounding, which then meant that the radius of curvature of the seat rows is on stage. The radius of curvature of the balcony is kind of on stage. It is problematic, which we then solved by having all focusing points in the middle of the room, kind of way above the heads of the audience. I think Winfried Lachenmeier basically was involved in that one. That's a full collaboration between Müller, BBM, and us. And the additional one here is that the balcony undersides are non-horizontal and the verticals are non-vertical. With here, what we're using is they're relatively small, and we're doing a different angle for both. So the lower reflection goes to another part of the audience than the upper reflection, so that you really cover everything. But what I want to get here is a canopy. The rule here, we want to do radius of curvature. The architect had a different rule, which actually I find extremely interesting. It's always a line is a line and a line is horizontal. So in the balconies, this lower line of the balcony front is horizontal. And the lower line, the cornice line where both meet, where the underside meets the vertical reflector, is horizontal. But the balcony doesn't follow the sidewall. So the width of the balcony is different. So you have a height difference, but it depends on how wide the balcony is. And it's slightly warped, and then we had a discussion whether you can build it, but it's actually quite easy. And then the same was with this reflector. That's, yes, it's tilted in general, but basically the edge line is straight, and the middle line is straight as well, which basically means the height difference between the edge and the center is always identical, which basically means your radius of curvature is a function of the width of your reflector. And that's what we used here. That's kind of actually the acoustic reason why the front is wider than the back, is it's wider, so the radius of curvature is bigger. So the reflections for the strings are stronger than the reflections back to the brass that need them less. And it's actually quite fun. Yeah. And that was Juan Oscar's multiple. I mean, basically, that's what you can do now together with, that's all the acoustician designing. And then you can either say it's all the acoustician designing, but in a way, we are giving a catalog to the architect that then tells us what is the right thing to do and to then develop further. Good. And I think materiality. So all this is wood. I think you can hear wood. All that is plaster. I think you can hear plaster or marble, or you can hear a different tone color. And all that one is tiles. And in principle, that's even more brilliant, and that is glass. But here we compensated what it actually is. It's all mosaic stones in mortar. And then we just made sure that the mortar is a little bit absorbing, that you can kind of correct the frequency response. As I said, there is different ways to skin a cat, but sometimes some of the ways are not totally evident, but just think hard. Thank you very much.